Hello, and for the third experiment that you're going to do, you are going to do a hydrolysis reaction, and you're going to do the whole synthesis and analysis, so the full thing this time. And the hydrolysis experiment, or the hydrolysis reaction, literally means breaking with water. So we're going to start out with an ester that is shown here. If you've not gotten to it in lecture, it is a carbonyl group that is attached to some kind of alkyl group that we designate R, and through an oxygen to some other kind of alkyl group designated R prime. And in a hydrolysis, and hopefully you can see behind me without too much glare, if I combine that ester with water, the carbonyl bond is very polar. It makes a partial positive charge on this carbon atom. Water also is a very polar molecule. The partial negative charge on the oxygen of the water would attack that carbonyl carbon and causing it to break without going into the mechanism, causing it to break into eventually this very bottom piece here where we have a carboxylic acid and an alcohol. Notice that if I look at the components of these, the ester and the product has an R group, it has a carbonyl, has an oxygen, has the R prime, but now it's added in a water as it broke apart into these two molecules. Okay. When we get into the lab, we do things to make sure that the reactions go most efficiently and make the furthest amount of product that we can possibly make. So water and an ester eventually, to some extent, would react, but we don't want eventually and to some extent. We really want to get as much product as we can within the 3 hours that we got. So we're going to do a couple things to make that happen. The first is, instead of using just water, we're going to use sodium hydroxide, because that will totally fall apart in water. The fully charged OH group is going to attack much better than just a water molecule. In addition, we're going to heat it up to give it energy for the reaction. We're going to do that through a reflux, which you've just done for the ferrocene experiment. So we are going to boil it in solvent at a particular temperature for 30 minutes and get the most amount of product. By doing it this way, we are going to first create a carboxylate salt here. So instead of the acid, it will be ionized, it'll be negatively charged and paired with a sodium molecule, and we'll make that alcohol product. Okay. Just one other thing to note over here on the arrow, I have indicated the different things that are going on in this reaction. So we're heating it. We always want to indicate that. I'm adding sodium hydroxide in water. That's important. If you just added the solid sodium hydroxide, we wouldn't have what we needed. So it does have to be aqueous. And then ethylene glycol. Think about what purpose could that serve? It's not part of the product. So that's your indication that this is your solvent that is helping to determine the temperature of the reflux. So we've added that in to drive the reflux to be at the boiling temperature of the solvent, and chosen because that temperature is particularly useful for this reaction. Okay, so we're going to be doing this in two parts. We're going to first create this carboxylate salt. We are going to take advantage of its solubility. That's going to be our word for today. Solubility is going to be the tool that we use to separate things. And we'll use that for a bit before turning it into the carboxylic acid, which is the thing that you are going to purify and identify. The ultimate goal of this experiment is to identify your carboxylic acid and your alcohol and determine what ester it must have come from to identify the starting ester that you have. So first thing is we're going to hydrolyze this. So again, under reflux, you would combine your sodium hydroxide, ester, ethylene glycol, and water and heat it. I am going to make a side note about the sodium hydroxide, just a fun fact. So if you've taken biology and you've learned about the macromolecules involved in cells, our cells are made up of phospholipids. And phospholipids are fatty acids, so long hydrocarbon chains attached by an ester linkage to a glycerol backbone here. What that means in practicality when you're doing this in the lab, as you are measuring out the sodium hydroxide solid, if you were to get some on your hands and go over to wash it off, as good lab protocol would tell you, you'd notice that your hands are kind of soapy. And what's happening is that sodium hydroxide is perfectly happy to hydrolyze the esters in your phospholipids just as well as it is the ester that you put in the tube. So it's actually breaking off those fatty acid chains. And that fatty acid is the structure of detergents and soaps. So it has a polar piece that sticks out in the water and then this long hydrocarbon tail that digs down into grease to help break it up. So another term for this particular reaction is saponification, making of soap, just for that reason. So again, fun fact. So we go through. All right, so once we've achieved this, what you would notice in lab is being made is many of these carboxylate salts are quite insoluble in the conditions that you've got it in. Might come out as a solid. We would probably have to redissolve it in some water in order to do the following step. But again, we're going to leave it in that charged state for the next step that makes use of solubility. The new technique that you're going to use is liquid to liquid extraction. So you would choose two different liquids that don't mix with each other, that have different densities, and stay as two separate layers. So think oil and water that you've seen. In this case, and for the things that we're going to do in this lab, you're going to have one layer that is going to be aqueous and one layer that's going to be organic. Not 100% always true of liquid-liquid extractions, but it's true for what you're going to be doing. The resulting solution that you've got is already aqueous. Okay? We can assume, even though there are things dissolved in it, that the aqueous layer is pretty much 1 gram per mil or so in density. We are going to be doing the liquid to liquid separation with diethyl ether. And diethyl ether is a density of 0.713 grams per milliliter. So think of which would be on the top and which would be on the bottom. Okay. In this case, we're going to have the organic on the top, aqueous on the bottom. And so the two liquids are going to be chosen so that some things are soluble in one layer, some things are soluble in the other layer. That allows us to start, again, teasing these things apart. We're going to make use of that to try and pull this carboxylate salt out and away from other things that are in the mixture and to try and clean it up. So in that, let's think about where different things are going to go. I'm going to switch out of the show here to do this. Anything that is actually charged is going to be found in the aqueous layer. Okay, so let's see if I can move this. That sodium and hydroxide are ionized. They're definitely going to be in the aqueous layer. And our carboxylate salt is also going to be in the aqueous layer. It's still charged. Things that are very polar, so things with hydroxide groups that can hydrogen bond, like an alcohol, those are also going to be in the aqueous layer. Prefer it to the much more nonpolar organic layer. Ethylene glycol has a bit of nonpolar section here, but for the most part, it's going to be driven by those OH groups to also stay in the water. And those of you with cars may know ethylene glycol as being the main component of your antifreeze, and you know it certainly mixes well in water. So maybe a little goes in the organic layer, but most stays in the water. So really what this step is going to be doing, its main purpose, is going to be taking this ester, this unreacted ester that's in that stew, and pulling it up into this organic layer to get rid of any of that. There are two terms you use with liquid-liquid extractions. So when the thing that you want stays put and the different impurities are pulled off to the other layer, we call it washing. So this would be an example of a wash. If what I wanted, if I did an extraction where the salt moved from the layer I put it in to whatever else I added into the separation funnel, I would call it an extraction. So this is an example of a wash. The glassware that you use is called a separation funnel, separatory funnel. And it would have a stopcock at the bottom, and you would pour your dissolved carboxylate salt into it, add the ester. You'll have a video that shows shaking and venting and mixing this up and letting it settle out. And you can then draw the bottom layer out through the stopcock to keep it separate from the organic layer that's left in the funnel. You would always save your layers that you don't use, just in case you're wrong about where you think your stuff is going. So you would be holding on to that diethyl ether layer in the funnel as you go through the next step to make sure you've gotten the correct stuff before you would dispose of the diethyl ether layer. It becomes particularly important in the last experiment because you have several extractions and at least one that can sometimes flip top to bottom. And you always want to hold on to all your layers to make sure you've got the correct one. So at this step, okay, we've gotten this whole stew of stuff after the end of the reaction. We've pulled out the unreacted ester, and we want to do some further cleaning. So you would be pulling out the dissolved carboxylate salt, and now we're going to turn it into the carboxylic acid by adding a large excess of 6 molar hydrochloric acid. So remember that you've done this reaction in sodium hydroxide, a fairly good amount of sodium hydroxide, so it needs to be neutralized by the hydrochloric acid, and then also have enough extra that there are hydrogen protons to create this carboxylic acid. The carboxylic acid is solid. It'll precipitate out of solution. So in lab doing this, you would add the hydrochloric acid and get a very impressive amount of crystals forming at this point of the reaction. The alcohol would still be there, but staying in the liquid form. Okay. So in your beaker, you're going to convert that carboxylate salt to the carboxylic acid, again, adding an excess of acid for hydrogen ion. It's going to push this reaction to the right. Remember your Le Chateliers, so big excess of reactants pushes to the products, not to mention the product is solid and precipitating out and no longer is factored into the equilibrium of the equation. So it's pretty quantitative at pulling the salt out. One issue, though, is that as it comes out, it is capturing a lot of the ethylene glycol, the alcohol, other things that are in solution get trapped in those crystals as it precipitates. So what we first get is what's called crude crystals that we would vacuum filter. And to clean them up and get a pure sample of that carboxylic acid, you are going to recrystallize. The way recrystallization works is you find a solvent where the material is soluble in hot solvent, but insoluble in cold. And in this case, water works well for that. So we will dissolve the crystals in just enough boiling water to get them dissolved and then let them cool slowly. And what happens as they cool is the pure crystals are the lowest energy conformation that could be achieved. If an impurity were to get trapped in there during the equilibrium between crystallizing and being in solution, that impurity would get kicked out and leave just the pure crystals. It's usually quite visibly different from the crude crystals that look kind of gloppy, and then you get these pure crystals that are very needle-like and fine and look much more like a pure fine crystal. And you would again collect that by vacuum filtration and leave it to dry in a labeled container and wait for that so that we can analyze that now pure solid by melting point that we will talk about in the next series of videos. Okay, so this procedure now has gone through the majority of the purification. We'll talk about how you are going to analyze that alcohol. We have to give you some canned data for that because getting it pure enough for the analysis we do is extremely difficult. So at this point, we just have purified the carboxylic acid. That's what you'll focus your percent yield and theoretical yield calculations on for your report.